Okay, well, happy Friday, everybody. Week 7 Friday. I appreciate you being here. And for those of you who are watching the video, thank you for watching the video. Again, I also appreciate everyone's flexibility in just kind of changing the schedule a little bit. I have posted, we spent earlier today grading your midterm exams. And so those have been graded and your grades have been posted to Canvas. So that's that. If you have any questions or if you want to see your exam, you can come by in person during office hours, which are held on Mondays and Wednesdays after class. So, or I guess 11:30 to 12:30. So technically I give myself a little bit of a break between class and, well, anyway, all right, you can come by and take a look at your exams. And I also posted just a little bit about the grade distribution on Canvas as well. Overall, I think the scores were pretty decent. Median was an 87. Q3 was a 96. So a lot of high performing exams. Q1 was a 67. Which is a touch lower than what I would have liked, but overall, I think I'm happy with the overall performance of the class. If you have any questions or concerns, feel free to come talk to me. And if for whatever reason you did not perform as well as you would have liked, well, first, my first bit of consolation is that it is just one exam, and it's only worth 15% of your total course grade. So even if you say lost half the points or something, that's only 15% of the total grade. So half of that would be around 7.5%. So there's still a lot of other points in a lot of other things, in your homework and the other exams, as well as the lecture view quizzes. So lots of opportunity to make up points. And then the other part is what I always kind of say and harp on, and I don't want to discourage or upset anybody by saying, but you as a person, you are not defined by your grades or your academic performance. And of course, I get it. It feels good to get good grades. It doesn't feel good to get bad grades, but you are so much more, and don't allow your performance on one exam, or even if you're having a tough quarter and it feels like maybe in all of your classes you're not doing as well as you'd like, and sometimes we just have quarters like that. Don't let that change your perception of self, or your feelings about the subject or school or whatever it may be. So at the beginning of the quarter, I kind of gave a spiel about grades and life and all of that. And I still stand by that. And I know at the end of 7th week, and when there's just a short stretch left, and we're all feeling the pressure. So, but I hope we can kind of distance ourselves from this idea of grades and self-perception and all that. But if you did great, good for you. But don't tie yourself too closely to your own academic triumphs either. It's great to be proud of yourself and be proud of your scores, and that's fine. But yeah, just we're much more as people. Okay, we left off on Monday. We talked about support vector machines, and we went through a whole bunch of stuff. I mean, what was this slide about, right? We were talking about maximizing the margin, and we got to a point where we said we can solve this using quadratic programming, and effectively what we are trying to do is we are trying to find the correct values of alpha as far as what that directional vector is going to be that defines this boundary line, right? So we're looking for the boundary line that that defines this. We're looking for the vector that defines that. That's the W. We're looking for what that could be. And effectively, it comes down to figuring out what values of alpha to use. And basically, if the point X is not going to be one of the support vectors here, then the alpha associated with that point is going to be 0. Okay. And if it is going to affect the vector, then alpha is going to be some other value. And as it stands right now, the boundaries are just going to currently, with maximum margin, the maximum margin classifier, there's no limit to what alpha can be for the for each of these points. And what we can do is we can do the soft margin, and that effectively puts a limit to what that alpha can be. So we're still going to find some vector W that's going to create the boundary, but we're putting a limit on C, which is going to limit how much influence a single point can have on defining the boundary. So that if there was some kind of wayward point, it would create a, whereas with the maximum margin likely classifier, where no misclassifications were allowed, having a soft margin would allow one of the points to kind of fall on the wrong side of the boundary. And that's what this is. Okay, we're putting an upper bound, which is kind of how much influence a single point can have on defining the boundary. And that's kind of where we left off on Monday. And where we're going to take a look at today is we're going to say, well, you know what? If we look at this form as if this thing has much meaning to us, there's this part as because effectively, we're trying to maximize this function. We're trying to find the values of alpha and whatnot to maximize this kind of this inner product of x. And this, we can replace this inner product of x with something known as a kernel function, okay? So right now we have kind of xm transpose xn, and we're going to replace that with a kernel function k applied to xm and xn, okay? And this is kind of what does this even mean? What is a kernel function? And a kernel function is basically going to be an inner product or dot product of vectors after we apply some kind of transformation function to the original vector. So if the transformation function is basically nothing, if it's just the identity vector, right, identity function, then the kernel applied to this with basically no transformation function is just going to be the inner product or the dot product of xm and xn, right? So we get xm transpose xn, and that would be basically the same thing as kind of this inner product between xm and xn with no transformation function applied. But you can have transformation functions that will yield kind of some interesting results, okay? So for example, we can have this kernel function that's going to, or we can have this transformation function phi. Okay, so this function phi will take a point in 2 dimensions. We'll say a point exists at x1 comma x2. And after we apply this, it's going to project this 2-dimensional point into 3 dimensions. It's going to add a third coordinate, a third point, a third coordinate. And so now this point exists in 3 dimensions. So if we have x1 and x2, we can create a third coordinate, which is going to be x1 squared plus x2 squared. Okay, and this is an arbitrary function, but this is this is just one example that that can be useful. And when we do this, then when we say, let's do the kernel function, we're going to get an entirely new product. Okay, so here, let's say we have these 2 points, 1, 1, or 2 vectors, 1, 1, and 5, 1. Okay, xn is 1, 1, and xm is 5, 1. And we're going to apply this transformation function phi to this vector 1, 1. And so the transformation says, okay, you're going to have a coordinate, a 3-dimensional vector now, and it's going to have the x1, the x2, and the third one is x1 squared plus x2 squared. So we're going to keep 1, 1, x1 and x2 are still 1 and 1, but this third coordinate is going to be 1 squared plus 1 squared, which gives me 2. If we apply this transformation function phi to xm, we're going to keep 5 and 1. So we got 5 and 1. And then the third coordinate is going to be 5 squared plus 1 squared, and we get 26. And now the inner product of these two vectors, 1, 1, 2, and 5, 1, 26, is going to be 1 times 5 plus 1 times 1 plus 2 times 26. So I'm going to get 5 plus 1, and 2 times 26 is 52. So I get 5 plus 1 plus 52, and that gives me 58. All right, so this is the kernel function when we apply it to 1, 1, and 5, 1. Is that okay? What happened here? So I took my 2-dimensional point, I applied this transformation function, which makes it a 3-dimensional point, and then I take the dot product of these 2 points now that now exist in 3 dimensions. But I know right now it's kind of like, what's the point? Why are we doing this? Okay, we'll get there. We'll get there. Okay. So anyway, this is what we've done. Now, I can do this. I can take the point 1, 1, 1, 1, and 5, 1. I can turn them into 3-dimensional points, 1, 1, 2, and 5, 1, 2. And then I can take the inner product and I get 58. This thing, we also have, it's not actually necessary to figure out what this transformation is. Okay, so here we have the transformation function that goes from 1, 1 to 1, 1, 2 and 5, 1 to 5, 1, 26, but it's not actually necessary to use that transformation. We can take the kernel function, and the equivalent kernel function for that transformation is going to be xm transpose xn plus xm norm squared plus xn norm squared. So if you do this, you're going to get the same result. So, so if I apply the phi function to transform the vectors and take the inner product, I get 58. Or I can just have the equivalent form of the kernel function here, and we can say, well, let's do the coordinate 1, 1 transpose 5, 1. Okay, so that's going to give me 1 times 5 plus 1 times 1. And then we're going to take norm 1 square, norm x1 xm squared and norm xn squared, which is going to be 1 squared plus 1 squared times 5 squared plus 1 squared. Okay. And if I do that, so if I apply this kernel function to the 2-dimensional vectors directly, I get the same result of 58. And I kind of just want to pause here and just make sure this is okay and this makes sense. That what I'm trying to show is that what the kernel function is it's an inner product or a dot product of 2 vectors if we apply transformation functions to them right here. And sometimes there is an equivalent function that gives you the same results without having to actually transform the function, transform the points. Okay, so rather than having to go from 2 dimensions to 3 dimensions and then taking the dot product, you can actually take your 2-dimensional vector, plug it into this function, and get the results directly. So that's also possible, and that's what we have here. So here we get 58 and 58. Same results One, we transform them into 3 dimensions, take the inner product. The other, we're just applying the function directly. Let me give you your first view quiz answer. First view quiz answer is D, D as in dog, D as in dog. Okay. So the reason why we would want to do this in the first place, right? So we kind of did all of this weird kernel business. The reason why is what we can do is we can apply the kernel trick, and we can now form boundaries that are non-linear by projecting our 2-dimensional data into a higher dimensional space. Okay, and here is an animation that describes what.
Right now, you can join Planet B.
Okay, there's a commercial that's playing first. Let me skip this commercial. Okay, here is this animation. Okay, and basically, I'm going to just, okay, so I don't know if you guys can see this. Okay, there is a cloud of red points surrounding the outside, and then there's blue points in the inside of this circle. Okay, so you have blue points in here, red points out here, and it says they are not linearly separable. Okay, we can separate them with a circle, but we can't separate them with a straight line. Okay, because we've got red points on the outside, blue points on the inside, right? And if we were to try to do the maximum margin classifier or something, okay, you know, we can have these straight lines, but we're not able to separate them using a straight line. So how does this work? Well, what we do is we take the data, which exists in 2 dimensions. Okay, so here maybe you can see there's blue points here and red points here, and we're effectively projecting the data into 3 dimensions. Okay, and so this transformation is basically projecting it from x1, x2 into x1, x2. Those coordinates remain the same, but the third coordinate is x1 squared plus x2 squared, and that's what gives us this parabolic shape. Okay, so we're adding a third dimension, x1 squared plus x2 squared. And so points near the center end up low, but points far away where x1 squared plus x2 squared are large end up kind of projected high, have a high kind of third dimension, third coordinate. And now that we've added this third dimension, we can draw a linear boundary. This would be, I guess, a plane in 3 dimensions. A linear boundary in 3 dimensions is a plane, and this 3-dimensional boundary, or this linear boundary in 3 dimensions, now creates a non-linear boundary back in 2 dimensions that successfully separates the blue from the red. Okay, so once again, the animation shows that we have blue and red points that we cannot separate linearly, not with a single straight line. So we project it into 3 dimensions using some kind of transformation. And then once it's projected into a higher dimensional space, we can draw a linear boundary, and that will separate the classes, the blue from the red, in this higher dimensional space. Okay, does that kind of make sense? What we're trying to do here? All right, and so that's the reason why we're doing the kernel trick. Now, we actually, again, the point of this kernel function is we don't actually need to transform it and figure out what is the coordinate of every single point in 3 dimensions. We don't actually need to figure out this third dimensional thing. We can continue using just this kernel function. Okay, so going back to this slide, all we have to do is we just use the kernel function, and the quadratic programming that is able to figure out the alphas, the levels and alphas that minimize this thing, we can just use it here, except now we just apply the kernel function rather than just take the direct inner product. We just take the kernel function there. But that will be the same as kind of transforming it here, okay? So there's actually quite a few kernel functions that we could use, and you can go to Wikipedia, and there's all of these kernels, right? So the linear kernel is basically no transformations. You just, the kernel function applied to the vector x and y is just x transpose y, okay? There's the polynomial kernel, which will take x and y and will basically do x transpose y raised to some power n, okay? And then there is the Gaussian kernel, which will, when you apply the kernel function x, y, it basically takes the difference between x and y, x minus y, and it takes that difference and it squares it, and it raises e to the negative of that thing, okay? And then there's other kind of kernel functions and things like that. All right, so for some of these functions, the you know, in the case of this thing, this transformation function turns it into a coordinate in 3 dimensions, or length 3 vector, and we take the inner product. In some other kernel functions, it actually transforms the 2D vector, the vector in 2 dimensions, into a very high dimensional vector, okay? In fact, the Gaussian kernel, this one right here, the Gaussian, or also called the radial basis function kernel, the RBF kernel, radial basis function kernel, actually takes your vector and it transforms it into a vector of infinite length, okay, which is very difficult for us to comprehend, right? So this kernel back here basically transformed it and turned it, our 2-dimensional vector, into a length 3 vector, okay, length 2 vector into length 3 vector. That seems easy to understand. The Gaussian kernel actually takes our length 2 vector and transforms it into an infinite dimension, or infinite length vector, okay, based on the Taylor expansion of the exponential function, right? So we have an exponent, you know, you have the Taylor expansion of the exponential function, which is an infinite series, but we can say, oh, okay, that's the equivalent of e raised to some power, which is fine, but you know, we obviously can't comprehend a infinity length vector, and but that's effectively what the Gaussian kernel does. We don't actually have to figure out the infinite values in that vector, okay? We can just take this kernel function and it would give us the result, the equivalent result of transforming it into infinite vectors and then taking the dot product of those infinite length vectors, right? So if you take the dot product, you'll just get one value, and you don't actually have to figure out what that transformation is, okay? So that would just be an exercise in pain, and we don't have to do that. We just say, all right, well, what is this? What's the radial basis function? And we just do e raised to this thing, and that's going to give us the equivalent. So again, it's not necessary to actually transform the original vectors. We can just use the kernel function directly, which we are grateful for. So we don't actually have to figure out those things. And so effectively, it allows us to create these really non-linear boundaries between kind of, I guess, different classes that might be difficult to separate, okay? So the maximum marginal classifier was just draw a straight line. And now that we have this kind of tool that allows us to transform into higher dimensions, and then we also allow for things to fall on the wrong side of the class using the soft margin, we can now draw, you know, some curvier boundaries between our different classes. Okay, so here, this is some data we have. This comes from the textbook Elements of Statistical Learning, which is an excellent textbook, freely available, but it is fairly dense. So, you know, it's not exactly light reading, but if you're interested in more machine learning stuff, it's a good reference. Oh, before I get too far into it, let me go ahead and give you your second view quiz answer, which is the letter E, E as in elephant. E as an elephant is our second view quiz answer today. Okay, so here I'm going to just use the function SVM, okay, and it comes in this library called E1071. And I'm going to just start off with a linear kernel, okay? And when I start off with a linear kernel, it just tries to draw a straight line that's going to separate the two classes. I've got black and red, and it says, you want me to draw a straight line to separate the two classes? This is kind of the best line I can do. Obviously, we've got some misclassifications, but if we want a straight line boundary, this is what it's going to give us. Okay. We can use a polynomial kernel, okay? And so again, a polynomial kernel is this thing, and we're just kind of again applying some kind of transformation function to x or y, and that expands out, okay? But effectively, we don't actually have to do that transformation. We just do x transpose y raised to some nth power. Okay, so you do a degree 3 polynomial, and don't try to imagine this as being some kind of cubic function. It's not. What we're doing is we're, again, transforming the data into something higher dimension, right? So that the video animation was very good in that it went from 2D into 3D, and then we drew a plane. Now it's probably going from 2D to maybe something in 5 dimensions. Again, hard for us to visualize. And then it's going to draw a linear plane, a linear hyperplane in that 5-dimensional setting or high dimensional setting, whatever it is. And then when you project it back down into 2 dimensions, where you're basically looking at the shadow of it, this is the shape of the shadow. It's hard, again, hard for us to visualize, but this is it, okay? We can increase the degree of the polynomial, and we get something like this. This does not look very good to me, but that's what we get, okay? And you can kind of mess around, and I suggest that you do. I suggest that you kind of fiddle around with different values for the degree, different values for gamma, and things like that, and see what effect it has. I want to talk a little bit more about the Gaussian kernel. This is probably one of the most popular choices because it's very flexible. And there are effectively 2 parameters that we're going to mess with, the gamma and the cost, the gamma and the cost. The gamma is related to kind of how flexible you want, and the cost is kind of related to how much of a penalty is applied when you misclassify a point, okay? And so by default, I think, I don't remember what the exact default values are, but here if I use gamma 0.5 and cost equal to 1, this is the boundary that it draws, okay? And I think in the homework, which by the way, I've given you an additional 24 hours, so it's due tomorrow at 6 p.m. I think I have some example gamma and cost values. I encourage you to just kind of fiddle around and change that gamma value, change the cost value, and see if you can really kind of figure out what the effect of those parameters are on the SVM classification. There's also some videos on YouTube if you look up SVM, Gaussian kernels, and you know, the different parameters that probably explain it as well. But I kind of want you to try to mess around with it and come to your own conclusion first, okay? So experience it yourself, and then if you're still kind of at a loss for words for what's going on, sure, you can look up resources online, okay? But this is what we have. We have gamma 0.5, cost equal to 1, okay? Here, I'm going to lower my gamma to 0.1. I'm going to keep my cost at 1. So I'm going to keep the cost at 1. Here's gamma 0.1. Here's gamma 0.3. Here's gamma 0.5. gamma 1, gamma 2, gamma 5, gamma 10. Okay, so all of these, we kept the cost at 1. And how would you describe what's happening to our boundary? So we have this, and as I increase my gamma, what happens to the boundary? So what, just so you know what's going on, the thick line is the boundary. And then we have kind of like contours that are, these are parallel lines, but that exist in the hyperspace, okay? So they're not parallel once you project them back down into 2D, but in the hyperspace, they are parallel planes, right? So kind of like all the way back here, these are parallel lines, okay? We're effectively seeing the same thing here. These are parallel planes in the hyperspace, okay? So as we increase, you know, what's happening here, okay? So we get, you know, more of a curvier fit. One thing I like to kind of use as an analogy is, okay, so here I've got this HDMI cable, right? And it's kind of like this fat cable. So you can kind of think of it like an extension cord or something. And if I try to bend it, I can bend it, right? But it's not super flexible as far as like can I make really tight turns and corners? Like I can, but I have to like really force it to do that. Okay. Whereas if I take, say, like an iPhone cable, it's a lot more flexible, right? It's a lot more flexible. And I want to say, like in this very loose sense, changing the gamma from a low number is like having a fat extension cord that's like a little bit hard to, you know, it's like a hose. It's harder to flex this, to, you know, getting something that's like thin string or twine that you can kind of, that has a lot of flexibility. Okay, so that's all keeping the cost at 1. Here I'm going to keep the gamma at 0.5, and I'm going to start off with cost at 0.1. And then let's see what happens as I increase the cost. Cost goes from 0.1 to 0.5 to 1 to 2 to 5, now to 10. Okay. So what's going on here? So the gamma is kept at a low 0.5. And when the cost was low, it's, you know, very kind of, there's not a lot of tight turns here. Okay. As the cost goes up, okay, we're able to actually force the cable into a little bit of tighter turns. Okay. So it's kind of like saying each point is now applying a little bit more force onto the cable. Okay, with gamma being low, it's still, you're still using a fat cable, but with a high cost, each point is now able to kind of force a lot of pressure onto the turns. Okay, here gamma is 2, so we're already dealing with, you know, kind of more of a flexible cord. Okay, cost starts off low, and as I ramp up the cost, okay, so we go from cost 0.1 to 0.5 to 1 to 2 to 5 to 10. Each of these points are now able to influence even more. And so each point is now able to apply more force. And again, because we're dealing with kind of like a softer cord, we can get some even tighter and more kind of, I don't know what the right word is, more flexibility in the thing here. Okay, this is all with gamma equal to 2. Okay, and lastly, here I have gamma equal to 5. Cost starts off at 0.1. And so gamma 5, and as I increase the cost quite a bit, each individual point is now kind of exerting a lot of pressure. And now our boundary here with gamma high and cost high, we have boundaries that fit our data almost very, very, very well, right? There's very few misclassified points, like maybe these 3 red dots that are all by itself. But you know, these dots right here are able to kind of force their own boundary. And these red dots kind of force their own boundary. These black dots over here force their own boundary. And so we get this very, this boundary that fits our observed data very well, maybe a little too well. Maybe we are overfitting the data by having a high gamma and a high cost. Again, in our case with a high gamma, it's like having a very, very flexible boundary. Maybe like it's like using dental floss or something, this very soft with high flexibility, and the cost is very high. So each point is really able to exert a lot of kind of pressure. And is that the right move? Well, if you really want to avoid misclassifications, this is the resulting boundary that you get. Is this going to perform well in the future? I'm not convinced that it will. Okay. And I'm not sure, you know, obviously there's some noise here. And so does it make sense to have an enclave or an exclave or whatever? I don't remember what we established was the proper terminology here, but does it make sense to say this is not, you know, the red classification, right? So is this something a little bit better where, you know, this is our boundary? Do we want something, you know, what's the appropriate kind of boundary, right? Between, it does seem like there's some kind of pocket here that we should grow. And, you know, as we look at, you know, what boundaries make sense, I think there's kind of a few combinations that could kind of work, right? Gamma 2, cost 1, this seems decent. I don't know, you know, we end up getting this red zone out here, which I don't know if is right or wrong. We had no observations there. You know, as we're flipping through these, what is the boundary that we should use? And it's an open-ended question, but I do want you to kind of play around a little bit in your homework and see if you can kind of come up with a summary for explaining the effect of gamma and the effect of cost on the boundaries between the different classifications. Okay. Again, conceptually, what is happening that allows us to have such flexible boundaries is that we are taking our data that exists in 2 dimensions, but we are projecting them up into a higher dimensional setting. When we use the Gaussian kernel, they get projected into some infinite dimensional hyperspace. Really only the first few dimensions matter, just like the Taylor expansion of the exponential function. Really only the first few, maybe the first 5 or so are the ones that matter. But the point exists in that high dimensional space, and we are drawing a linear boundary there that then gets projected down into 2D. Okay, so you can continue rewatching this animation to see what's happening, right? So
People have been wondering.
Keep getting Planet Fitness commercials. They opened a Planet Fitness near my house, and I think I'm in the targeted category. So anyway, this is what we have. It gets projected up, and we're drawing a linear boundary there. Okay. We don't need to actually figure out the transformation function. I know for a lot of people, it feels comforting to know what the transformation function is, but you don't actually need to know it. Okay, that's all I have for today. We'll go ahead and end here. Thanks for joining me online. Let me give you your last view quiz answer, which is the letter A as in apple. And we will end here. Have a good weekend. We'll see you on Monday. It's already the end of week 7. We just have a couple weeks left. Oh, I sent out an email. In 2 weeks, we'll have a guest speaker, Alex Krebs from Meta, data scientist at Meta, and he'll be there to kind of share about his experience and answer your questions about, what life is like in the corporate world, what the job hunt and what all of that process is good, or what it's like. And so, submit your questions, and I hope it's a good time. All right, have a great weekend, and we'll see you later.